All right, so for part 3 of chapter 11, sections 6 and 8, I'll skip the one, this is 7, it's kind of a separate item. So complex power. I'm going to just throw up the definition here from the text because I think it's a good one. The product of RMS voltage phasor and the complex conjugate of the current phasor, right? We've been seeing that even with I squared or V squared, you're really talking about V times V conjugate, complex conjugate, and that's what we're doing here. So they're the conjugates and whatever, and as a complex quantity, the real part is real power. Now we're calling it P, and the imaginary part is reactive power. We're giving it some names. Okay, we're giving it some names. So you'll see these two terms now come along. And we're going to talk about them as though they're real and reactive. Okay, so just a few things. Here is this definition in terms of this. Here's this definition in terms of power, right? We're used to seeing that. Here it is right here as RMS values. So here's that complex power, right? How do these two relate, right? What's going on here? Remember, I could break this up as V over the square root of 2 and I conjugate over the square root of 2, right? And I would get square root of 2 times square root of 2 is 2. So this can be broken up like this. And that's and now these suddenly look like RMS values. Okay? And that's in fact what's going to happen. 1 is the square root of 2. So now let's take it a step further because this V is really, right, a magnitude value at an angle. So now we're bringing back that angle and we're just calling this, the definition of it, to be the RMS, to be the maximum value over the square root of 2. That defines the RMS. And then we're adding to it the phase angle for the voltage. We'll do the same for current. Okay, so not a lot of big math there, just introducing these terms, and we're going to be bringing back the phase angles, right? That's the phasor part of this. So here we are with apparent power. And it's the product of these RMS values, right? There they are. We're going to have this current and this voltage now fully represented with their phase angles. And that's apparent power that we talked about in lecture 2. So now if we stretch that out, here's the full representation. I did this with the vector picture, right, where we had VMS times the cosine, that's the real part, right, the real projection. And here's the, we're now going to call it reactive, right? Those are the terms that are going to get used here in this business, okay? So here's our apparent power. Notice we've got a couple of ways to represent it. If we represent it as we have before, here's our I squared RMS times Z now. And if we use voltage, we use the complex conjugate. Well, this is back to the same thing we've seen before, except we're now using RMS values in their conjugate form. So these actually have phase angles associated with them, right? Just like they did up here. The phase angles are there. So let's stretch it out a bit here then. We're going to define the apparent power in terms of, the reason it's written out this way, because we want to define it this way. Here's Z. Here's Z being spread out, right? Z. It's actually a real part and an imaginary part. And this leads to real power and reactive power. Okay, just a lot of ways of continuing to define it. So notice this Q is going to be this thing, right? Q is the VRMS times IRMS, oh, but it's at an angle, right? And the same thing is true with the real. It's going to be at the cosine angle. Okay? So we're now breaking the power into real and imaginary parts. So Q is the thing that's going to control how good or how bad it is in terms of delivering real energy. Q is the killer. So if Q is 0, like this, if Q is 0, you got a unity power factor. Why is that? Because P equals S, right? If Q is 0, there's no Q involved, so P equals S. And the power factor is P over S, which is 1. Doesn't get better than that. Okay? Now we define two terms. If Q is, because Q can be plus or minus, right? There's a sine wave involved, and it can be plus or minus. So that's the reactive term. It turns out by definition, we're calling these things, and there's a bit of visualization with it too. If Q is less than 0, in other words, it's a negative number, this results from capacitive loads. We call that a leading power factor. And why would that be? Here, look. If I've got my cosine wave, right? And I say Q is less than 0, right? Then that means something is happening over here. So the Q reaction to this is over here, right? And if this is a time axis, what? This guy, the dotted line, happened first. This happens first, and this happens next. Okay? So if Q is negative, that means time got pushed earlier, so something was leading. All right? And if it's positive, it means it happened, what? Over here, dot, 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 dot. So this would be later yet, right? So if Q is greater than 0, just think about it. If you're adding time, if you're adding something here, you're delaying it in time. You're saying, no, the time has to come to that level before it counts. So we just call that then lagging because it happens later. I will restate then, you saw this already, the complex power in volt amps. So now I'm going to emphasize this term, volt amps. And the installation guys and the power people and electricians will talk in terms of volt amps. That's the product of RMS voltage, a voltage phasor, and a complex conjugate current phasor, right? So phase angle is back in the game. And so here we are with our real and reactive things. There's that kind of a nice summary piece. I copied it here that lists all of this complex power, its apparent power, and it's real plus reactive, and it's the RMS voltages and currents with those being complex conjugates of each other. Okay, and here's all the details of that, right, repeated for us. We've derived a lot of this and run through it. Here the real power, this just breaks it out nicely because you can see real power is the projection on the real axis, and reactive power is the sine wave is a projection onto the imaginary axis when you think of complex numbers. And the power factor is just the difference in those angles. Again, even if those angles are not originally, neither one of these angles has to be 0. But because they're periodic signals, they will at some point, you could register one as 0. Okay, so that's a complex power. And then let's look at let's look at power factor, and we'll close the chapter with this. We talked about power factor, and we said if the power factor is near 1, that's a good thing because you're delivering a lot of real power. If it's far from 1, you're losing a lot of power somewhere in transmission, in the load, whatever, and we don't like that. So, but it turns out there's ways to correct it because we have leading and lagging. We can change the sign on the reactive power. Okay, so let's just take a simple typical load. Here's our voltage applied and the current in the load, and I'm going to call it an inductive load because that tends to be the lagging power factor. Okay, and so also I like that the book chooses this because most loads in the power industry are inductive, to be honest with you. Just look around. You see transformers, you see motors, you see transformers in microwaves, in ovens and stoves and all that. The transformer's kind of there, and it's nothing but a coil, right? There's the inductor. But because there's a lot of wire, we know from earlier courses there's a bunch of resistor. It's very hard to make an inductor that has no resistance, okay? So the two are always kind of go together, and you hope it's mostly inductance when you're making like motors and that, because too much resistance is just going to make the motor hot. You got enough heat being generated by friction and rotation and all that anyway. But this is a really typical load on a power source. So if that's the case, you know from what we just got done talking about with real and reactive loads, you don't want a lot of reactance in the load because you tend to waste power. That makes the angle, the phase angle, big. Okay? So what we want to look at is what can we do about that? Here's power in this case. The apparent power is, the real power delivered is S1. Whoops, the real power delivered is S1 times the cosine. Okay, remember P. We don't want to forget the terms. This is real. Right, that's what the P is about. To go along with it, we've got some imaginary power. Right, this is the reactive power now. And it's just the apparent power times the sine. And we're only dealing with one theta, one angle, because we only got the one element here. Okay, and those two are related by the tan. This is just trigonometry going on here. So you can relate real power to reactive power. That's just looking around the triangle, right? Okay, so now let me go ahead here with this. I want to show you. Here is that picture, and I've taken the one out of the text, but I'm going to develop it a little bit, a piece at a time. So here is the inductive load. Here's the load, right? This is the load up here in our simple circuit. the motor on there. That's the current coming out of the source. Okay? That's the current out of the source. And it's at some angle, theta 1. That's this angle in here. This angle here is our theta 1. Okay? Now, if it gets big, and we look at the projection onto the real axis, the bigger this angle gets, the more this pulls down here, the less and less real power we're going to have. Okay, so we'd like to get away from that. So how can we do that? If it turns out if we add a capacitor on, so remember right away we're thinking this is what? Plus Q, this is minus Q. All right, so we're going to try to add these so that these two, I'll say fight each other, but they oppose each other. And maybe they you know, you could call it complement, except that we're talking about power. We don't want to waste a lot here. Well, but we're not trying to make IL 0. We're not trying to make IC 0. We're trying to make the combination of reactive power that both of these consume together, we're trying to make that go to 0. We're trying to change that amount. Okay? So the way we do that is we're going to add on this capacitor. And if we think of it, look at this. Why is it just pointing vertically? Why isn't it off at some strange angle here? The current in the inductor is off at some strange angle. It's not pointing straight down. It's pointing off at some angle. Well, it's pointing off at some angle because the load is made up of a resistor and an inductor. So there is if there was no resistor, the inductive load would be right down here. All right? But there's a resistor that's pulling it this way. The capacitor has no such animal. And this tends to be true. Capacitors, because they're not wound coils or anything made of lots of wire, the capacitors tend to be free of resistance. So here it sits on the imaginary axis vertical. Okay, it's just going to draw current, but at plus 90 degrees. So you can already kind of see these two pieces, these two vectors are going to work together. And in fact, you know, they're going to be added together. In fact, we could take the vertical capacitor current, and if we knew the vertical inductor current, we could just, you know, subtract those two. But we're going to do that as vectors anyway here. Okay? So let's take the next step and do that vector addition. So look what happened. Here we did it. We took the, if I projected over here and got the inductor current down here, what did I do? I said, okay, the inductor current is down there. I'm just going to add the capacitor current to it and create a new vector. So there was my phase 1, or my phasor, theta 1. And here's now the new one, theta 2, because I took some of the current that went into the inductor and I balanced it with current going into the capacitor. So from the power point of view, I've dragged the current out of the source. Right? This is the source. Here's inductor current down here. Right? I've taken the source. The source current is now less. See, this is the source. It's not so bent. Okay? This isn't the best illustration here of IL. IL is actually over here. Okay? This is the source current in that inductor only load. So in a way we could rub that out. That isn't the source current, but now we've moved the source current back here. Okay, so keeping the picture in mind of what's happening with correction. We know we've already moved to a smaller angle. So we know that we're going to have less total reactive power. That's got to be a good thing in terms of power factor. Let me look at it. This is the same situation that the author has drawn this. The same situation, except he's now just said, all right, let's just talk about it as trigonometry. And what's going on is this was the original Q associated with a theta 1. Now I'm going to have a new apparent power associated with theta 2. In order to do that, I need to know how much reactive power do I need to supply or consume with the capacitor. Okay, and if I know that, I'll be able to calculate what size capacitor I need. So here we have the capacitor is the reactive power that the capacitor is responsible for. It's the reactive power divided by what? Omega V squared, and it's got to be the RMS version, omega V squared. Now where on earth did this come from? All right, well, think about what the inductance, if I take Z sub C, if I want to get Z sub C, right, what is that? It's 1 over omega C, right? So if I now say, well, what's reactance? The power is going to be that VRMS squared, right? The power is going to be VRMS squared, V squared. What is power? When you know the Z, divided by Z squared. All right, so it's going to be divided by Z. So it's like I squared Z or V squared over Z, right? So now if I were to solve this, where this is 1 over omega C, right? If I was to solve that for C, I'm going to end up back here with this, right? This is Q sub C, right? So Q sub C, multiply both sides by this, I'm going to get Q sub C over omega C is equal to that. And if I just solve then for C, I'm going to get back to this. Okay, so that's all that was going on to get me this. But when you look at things in terms, that's to find how much capacitance should I put in there. But when you look at it in terms of, okay, now it's just a vector diagram. It's just a phasor diagram, right? I can look at all this in terms of tangents. The tangent of theta 1 and the tangent of theta 2. That gives me how much Q I need, right? There's other ways to come up with the value of Q sub C, right? But what is this doing? This is basically, if you broke this out, you could say P of tangent of theta 1 divided by this minus P times tangent of theta 2 divided by this. You know, there's a lot of ways to do the math here with this, but it's really just working with the trigonometry of this simple diagram. And it goes back to the same thing we did here, okay, where we literally took and laid them out on a real and an imaginary axis and say, what's happening to those currents? Why does this even work? It's because I'm able to take current here that's at a different angle than the current here. And so I basically do the angle of the current here is different from the angle of the current here, and it's a corrective angle. So it basically straightens up the current here. it doesn't mean more or less power got delivered here. In fact, it cost me power to do this. But it makes the whole system more efficient. Okay? And that's what we're after. The same thing can be happen with the inductor, right? You get VRMS squared over X sub L, but that's omega L. So you notice omega times L here, and omega, what did I have? Oh, it would have been omega times C, but then you'd solve for it. Okay, so we end up with a solution for, we can follow that through to get to L. Right, L is this, you're going through the same process, right? But here it's the voltage divided by omega times the reactive power. Here it's the reactive power divided, but that's simply a reflection of this. Z sub C is 1 over omega C, whereas over here, Z sub L is, right, the direct comparison of omega L. So that's why, you know, the omegas, the Q's and L's, I mean, these two basically just reversed, right, from what they were over here. And that's simply a reflection of how the Z is defined. Okay? So that's what I want to say. That's what I want to say about, you know, phase correction or power factor correction. You're really just doing an angle correction. And you do it because you can take advantage of, you know, right here, I can put a load, so the constant in all this is the voltage across both the intended load and the corrective load. The voltage stays the same. You can do this in a parallel case. Okay? So that's it for Chapter 11, the 3 videos, and we'll pick it up in Chapter 12.